Welcome to our channel with new interesting episode. There are many unusual celestial bodies scattered across the universe, with some turned into mysterious anomalies by various factors. These include exoplanets similar to Earth, worlds never exposed to sunlight, planets engulfed by continuous sandstorms, and oceans with glowing ice bottoms. In multicolored nebulae, giant stars can swallow entire planetary systems, and jellyfish galaxies move through space with their shining stellar tentacles. Before exploring beyond our solar system, we must select Earth-like planets using the Earth Similarity Index, ESI. The ESI, based on a planet's radius, density, and average surface temperature, helps estimate mass, chemical composition, gravitation, atmosphere, and potential for liquid water. Earth, with an ESI of 1, serves as the standard. Celestial objects fall into three categories based on ESI. Objects with an ESI below 0.5, like gas and ice giants, mostly inhospitable. Those with an ESI between 0.5 and 0.7 resemble Earth more closely but might still be unfavorable for life. The third category, with an ESI above 0.7, includes planets beyond our solar system. Among them is Tigodon C, a rocky planet orbiting a red dwarf 12.5 light-years away, though its surface conditions are not hospitable. Due to its parent star's low luminosity, Tigodon B receives 63% less energy than Earth gets from the Sun. This results in an average surface temperature of about -47 degrees Celsius, too cold for life as we know it. However, there might be vast oceans of salty water beneath a layer of ice, similar to Jupiter's moons. Tigodon C, the inner planet, is the most Earth-like found so far, with an Earth Similarity Index, ESI, of 0.95. Just 0.05 less than Earth's ideal score. It orbits 0.025 astronomical units from its star, completing an orbit in about 5 days. This planet lies within its star's habitable zone, receiving 15% more radiation than Earth does from the Sun. Tigodon C likely has a rocky composition similar to Earth, with a metallic core, silicate mantle, and thin rocky crust. Its average temperature of 28 degrees Celsius suggests conditions suitable for liquid water and potentially supporting microbial life. Despite its promising characteristics, Tigodon C faces challenges such as its tightly locked rotation to its star and the red dwarf's occasional flaring, which affects its climate unpredictably. However, its potential for life remains high, showcasing nature's adaptability in extreme environments. The rogue planet resembles a cooled-off gas giant and must be at least 1 billion years old. It's mostly made of hydrogen, but in 2016, the Gemini Observatory found evidence of large amounts of water in its atmosphere. Scientists believe water condenses into clouds of tiny ice particles. It's still uncertain how this object formed. Researchers propose two theories. First, a celestial object like this might begin in a chaotic planetary system, where gravitational interactions kick out at least one planet. Alternatively, it could form like a star, from compressed interstellar gas, but with too little mass for nuclear reactions, making it more like a gas giant or brown dwarf. Some debate whether these objects should be called rogue planets or sub-brown dwarfs. Another term suggested is PLO, for interstellar wanderers without nuclear activity. Based on current understanding, YS0855-0714 has a mass estimated between 3 to 10 Jupiter masses, enough to trap heat effectively in its thick hydrogen atmosphere and metallic hydrogen core. Research suggests its surface temperature could support liquid water in its atmosphere as tiny droplet clouds. Mathematical models from the University of Edinburgh estimate its surface temperature around -23 degrees Celsius. This atmosphere also has a warm layer, about 100 kilometers thick, with densities similar to Earth's conditions, possibly favorable for potential organic life. In 2020, a candidate for a rogue planet was detected using gravitational microlensing techniques, awaiting confirmation. This object, possibly Earth-sized, lies between 30 to 180,000 light-years away. Such objects likely formed in a planetary system's protoplanetary disk but were ejected due to space cataclysms or neighboring massive stars. These rogue planets may remain isolated for billions of years, slowly cooling until they are consumed by black holes or destroyed in cosmic cataclysms, taking their secrets with them. This shows that the exoplanet PSR B1620-26c wouldn't have survived a supernova, which must have occurred before the pulsar PSRB 1620-26 was formed. Therefore, the exoplanet likely formed after this massive event, using materials from the nebula left after the explosion. Another theory suggests that the pulsar may have formed from the merging of two white dwarfs, a process not always accompanied by a powerful blast. Since this is the first such object discovered, science can't definitively explain its origins. This system, located 2,300 light-years from Earth, has a mass roughly 4 times that of our planet and an orbital period of about 66 days. The pulsar emits extremely powerful radiation, strong enough to destroy any approaching spaceship. Despite its dangerous properties, PSRB 1620-26c isn't considered the most hazardous exoplanet known. Kepler 70b, for instance, is even more dangerous. It is the hottest exoplanet known, orbiting the subdwarf star Kepler 70, with a surface temperature higher than our Sun's, reaching 6,800 degrees Celsius. Its mass is 0.44 times that of Earth, with a radius 0.76 times that of Earth, and an orbital period of just 345 minutes, or less than 6 hours. Interestingly, Kepler 70b regularly passes another object in the system, Kepler 70c, at a distance of only 240,000 kilometers. This close passage is the smallest distance ever recorded between planets. The high temperature on Kepler 70b may be because it was once part of its parent star. However, more evidence is needed to confirm its status as an exoplanet. Another extreme exoplanet is WASP-12b, which lies 870 light-years away. Its radius is 1.93 times that of Jupiter, with a mass of 1.46 Jupiter masses. WASP-12b orbits very close to its parent star, at just 0.03 astronomical units, causing temperatures up to 2,200 degrees Celsius. The host star's strong gravity slowly pulls WASP-12b closer, and it's expected to be destroyed within 10 million years. Studying such worlds may not be a high priority for scientists, but they often reveal unique features. For example, HD 189733b, though it looks similar to Earth, has extremely hazardous conditions with winds carrying silicate particles at 8,700 km per hour and glass rain. This gas giant orbits an orange dwarf in the constellation Vulpecula, just 63 light-years away, and has a diameter 1.1 times that of Jupiter, with a mass 1.13 times that of Jupiter. Its surface temperature can reach 930 degrees Celsius on the day side, never dropping below 425 degrees Celsius on the night side. HD 189733b has a foggy atmosphere with particles of iron, silicates, and aluminum oxide, and contains water vapor, neutral oxygen, and methane. It may even have an unknown activity in its atmosphere. Gliese 1214b is an ocean planet, discovered 42 light-years away from Earth. Its diameter is 2.5 times that of Earth, and it is 6.5 times heavier. It orbits very close to its host star, just 2 million kilometers away, with an orbital period of 36 hours. The planet's surface temperature is extremely high, possibly reaching 553 K, 280 degrees Celsius. Spectroscopic investigations of its atmosphere are inconclusive, but it's believed to predominantly consist of water vapor. The atmospheric pressure at the ocean's surface is incredibly high, with the bottom made up of dense and heavy ice, likely over 5,000 kilometers thick. The core is made up of rocks and metals. Although the chances of life evolving on such a planet are slim due to a lack of necessary microelements, studying ocean planets remains scientifically interesting. The Orion Nebula, located 1,344 light-years away, is the closest stellar nursery to Earth. It contains around 3,000 stars and giant clouds of interstellar gas, all interacting within an area about 23 light-years in diameter. The trapezium, an open star cluster within the nebula, contains several massive stars, including Theta 1 Orionis C, which is about 40 solar masses and 250,000 times more luminous than the Sun. The Orion Nebula also contains protoplanetary disks and protostars, indicating ongoing star formation. The James Webb Space Telescope has provided detailed images of these regions, revealing structures like Herbig-Haro objects, created by the interaction of stellar winds with surrounding gas clouds. In summary, These distant celestial objects offer valuable insights into the processes of star and planet formation, despite their extreme and often inhospitable conditions. Around 400 celestial objects have been discovered in the Milky Way, with an estimated total of 150,000. Among these objects are the bullets in the Orion Nebula, which are hundreds of astronomical units in diameter and move at high speeds, creating shock waves in hydrogen clouds. These bullets, containing iron that glows in infrared, are about 1,000 years old and of unknown origin, possibly resulting from a catastrophic event. The Orion Nebula is part of a larger cosmic structure called the Orion Cloud, which spans hundreds of light years and encompasses the entire constellation of Orion. Notable features within the Orion Cloud include the Horsehead Nebula, a dense dust cloud, and the Barnard's Loop, an emission nebula formed by a series of supernova explosions. The Orion Nebula itself is a fragile and unstable object, losing its material due to stellar winds, light pressure from young stars, gas emissions, and turbulent vortices. In about 100,000 years, it will disperse entirely, leaving an open star cluster. Among the fascinating exoplanets are K2-141b and KELT-9b. K2-141b is a rocky planet with a lava ocean on its day side and freezing temperatures on its night side, creating extreme winds and fiery rains. KELT-9b, a hot gas giant, has a surface temperature comparable to stars, and its proximity to its parent star causes it to gradually lose its atmosphere. V391 Pegasi b is a gas giant that survived its parent star's transformation into a white dwarf. This planet's resilience is remarkable, as it orbited close to the star's outer layers during its red giant phase. Pulsars, like the one 4,000 light-years away, are neutron stars emitting lethal radiation. The exoplanets orbiting these pulsars, exposed to intense radiation, highly inhospitable. CW Leonis, a red giant located 650 light-years away, has a radius 560 times that of the Sun and emits energy 8,500 times greater. It is surrounded by a complex nebula of gas and dust, formed from the star's material loss. CW Leonis' unstable reactions and material loss indicate a dramatic end, with its potential planetary companions likely long gone. The star's nebula, containing around 70 different chemical compounds, highlights the rich and varied chemical processes in the cosmos. CW Leonis, a red giant star, is notable for its high water content in its outer layers, a surprising discovery that challenged existing models of stellar evolution. Originally expected to consume icy comets as it expanded, observations in 2009 revealed temperatures reaching 1000 Kelvin, indicating the presence of water vapor forming directly in the star's upper atmosphere. This contradicted earlier models, which suggested all oxygen in stars of this type should have been converted to carbon monoxide, leaving no oxygen available for water formation. A new hypothesis proposed that ultraviolet radiation destroyed silicon oxides and carbon, releasing oxygen that then reacted with hydrogen to form water vapor. However, questions remained about the source of the ultraviolet radiation required for this process, as stars typically block cosmic rays capable of generating such radiation. It was suggested that unstable regions on the star's surface allowed UV radiation to reach the outer layers, facilitating water vapor formation. Despite its abundance in the star's atmosphere, water vapor constitutes a minuscule fraction of CW Leonis' total mass, highlighting its enormity. Estimated at several quintillion tons, water vapor is only a billionth of the star's overall mass, underscoring the scale of these celestial bodies. Currently in its later stages as a red giant, CW Leonis is expected to deplete its nuclear fuel within the next 10,000 to 30,000 years. After shedding its outer layers in a dramatic explosion, it will transform into a white dwarf, a dense and faint remnant with about 80% of the Sun's mass but several million degrees in temperature initially. The explosion of CW Leonis as a supernova will contribute to the creation of new elements, enriching the universe with substances like uranium and gold. Over billions of years, the remnants will cool, eventually becoming nearly invisible as a black dwarf, marking the end of its stellar life cycle. In conclusion, CW Leonis exemplifies the dynamic evolution and eventual fate of stars, contributing to the universe's continuous renewal and diversity of celestial bodies through its dramatic life cycle stages. There's a star called S62, a fast-moving white-blue star, located 17.8 astronomical units away from a black hole at its closest point. It moves at 6.7% of the speed of light, making classical mechanics inadequate for describing its trajectory due to relativistic effects. Its orbit axis shifts by 75 angular minutes per orbit. In the vicinity, there are several large star clusters totaling about 1 million solar masses. Further out, about 200 light-years away, another massive black hole likely exists, with a mass about 100,000 times that of the Sun. Moving further, we encounter the central molecular cloud, spanning 1,600 to 19,900 light-years with a mass over 60 million solar masses. This area contains stellar nurseries, gas nebulae, protostars, and remnants of supernovae. The cloud primarily consists of dense hydrogen with temperatures ranging from -223 degrees Celsius to 327 degrees Celsius. Moving towards the Milky Way's center, we find a bulge, an elliptical-shaped formation stretching 10,000 light-years in length and about 7 light-years in diameter. Its mass is about 10 billion times that of the Sun, with countless stars blending their radiation, making exact star counts difficult. The bulge extends into a bar shape, stretching about 13,000 light-years, serving as the base for the galaxy's spiral arms. Within one of these arms lies the star cluster Stephenson 2, home to the largest known star, Stephenson 2-18, which is 2,150 times the radius of the Sun. The galactic center hosts billions of stars and possibly exoplanets, although the dense stellar environment and radiation make habitable planets less likely there. The galaxy's habitable zone, a ring-like region 22,000 to 29,000 light-years from the center, offers more favorable conditions for life to emerge. Moving outward from the center, we reach the Milky Way's galactic disk, composed of the thin and thick disks. The thin disk spans 1,000 to 1,300 light-years in thickness and extends up to 50,000 light-years in radius, containing about 80% of the galaxy's visible mass. The thick disk, 4 times thicker than the thin disk, consists of older stars and little interstellar gas. Observations suggest that the Milky Way merged with another galaxy, Gaia Enceladus, 11 to 8 billion years ago, contributing stars and gas to form the thick disk and trigger a stellar baby boom. The galaxy's spiral arms, like the Scutum Centaurus and Perseus arms, are regions of high star formation due to concentrated interstellar gas. These arms, including the Orion arm where the solar system resides, span tens of thousands of light-years. Beyond the galactic disk lies the halo, a vast and sparse component stretching up to 260,000 light-years from the center. It contains old globular clusters, stellar streams like the Sagittarius stream, and significant amounts of gas and dark matter, contributing to the galaxy's stability through gravitational interactions. The halo also hosts the Great Rift, filled with dense interstellar gas and dust, potentially future sites for star formation. It extends up to 2 million light-years and remains a mystery due to its minimal electromagnetic radiation emissions. This overview captures the diverse and expansive nature of our Milky Way galaxy, from its central regions to its outer reaches, encompassing various stellar formations and environments. Distances between the Milky Way and other galaxies are incredibly vast, ranging from millions to billions of light-years due to the universe's expansion. This expansion causes the light from distant objects to appear redder than it actually is, known as redshift. Some galaxies, however, show blueshift, meaning they are moving towards us. One such galaxy is M86 in the Virgo cluster, about 52 million light-years away, moving towards the Milky Way at 244 kilometers per second. It sheds interstellar matter, leaving trails of warm hydrogen. M86 likely collided with NGC 4438 in the past, and has absorbed many smaller galaxies. ESO 137-001, 227 million light-years away, is part of the Able 3627 galaxy cluster, moving towards its center at nearly 2,000 kilometers per second. It creates huge gas tails up to 260,000 light-years long, where star formation bursts occur. The baby boom galaxy produces about 4,000 stars annually, much more than the Milky Way. It's located 12.2 billion light-years away, offering insights into the early universe's star formation. The Sombrero Galaxy, M104, 30 million light-years away, has a dust ring where young stars form. It also emits powerful X-rays from a supermassive black hole at its center. M64, also known as the Black Eye Galaxy, 17 million light-years away, has a unique structure due to a collision of two smaller galaxies. It features a dust band obscuring its center and rotates oppositely in its inner and outer parts. The Solar System, with Neptune as its farthest known object at 30 astronomical units, includes over 1 million small bodies like asteroids. Nearby stars include diverse types, from brown dwarfs to bright stars like Sirius. GJ 832c, 16.1 light-years away, is a potentially Earth-like planet, though unreachable with current technology. The Solar System is part of the Orion arm within the Milky Way, containing billions of stars and potentially trillions of planets. The Milky Way is part of the Local Group, which includes Andromeda and Triangulum galaxies. Andromeda, 2.5 million light-years away, is the closest major galaxy. The Local Group is part of the Virgo supercluster, containing over 30,000 galaxies. Laniakea is a supercluster of galaxies, including the Virgo supercluster and the Great Attractor, about 520 million light-years across. It's part of the cosmic web, immense structures of galaxies, filaments, walls, and voids spanning billions of light-years. The observable universe, expanding continuously, is about 93 billion light-years in diameter. Beyond it lie hypothetical extragalactic objects, challenging current scientific study. Some astronomical anomalies suggest massive structures beyond the observable universe, influencing cosmic motions. Speculation about what lies beyond includes metaphysical ideas due to the limits of scientific observation and physical laws. This summary captures the fascinating complexity and vastness of galaxies, structures, and the universe itself, offering a glimpse into our exploration and understanding of cosmic mysteries. This idea suggests that our observable universe, known as the metagalaxy, might be just a small part of a much larger and more complex superstructure in space. The dimensions and makeup of this superstructure are so vast and intricate that they surpass our ability to fully comprehend. It's possible that this structure exists in dimensions beyond our usual three or is governed by physical laws completely unknown to us. This would mean that our universe is just a tiny component or reflection of this astonishing superstructure. Some interpretations of the anthropic principle propose that beyond the observable universe, there could be other worlds where fundamental constants like the speed of light or the charge of electrons differ vastly from ours. This idea aligns with the concept of a multiverse, which envisions multiple universes like bubbles in a foam, each isolated by impenetrable walls. In each universe, the physical laws could be entirely different from what we know. More extreme hypotheses even suggest that our entire universe might be a simulation, akin to advanced virtual reality created by superintelligent beings or civilizations beyond our current understanding. Such ideas imply beings far more advanced than us, with goals and abilities that are mysterious and incomprehensible. These hypotheses are speculative and currently impossible to prove or disprove. The vast distances in space challenge our imagination and can seem infinite to human perspective. What we do know is that the universe is expanding, and this ongoing process suggests a future where distant celestial objects gradually vanish beyond our reach. Eventually, the universe might enter a state of eternal darkness, with no observers left to witness it. Ursula K. Le Guin, in her writing, reflects on the cycle of creation and destruction, suggesting that darkness is necessary to appreciate the beauty of stars. This parallels the birth and eventual demise of all things in the universe, from fleeting subatomic particles to long-lived stars, each with its own finite existence. The origin of our universe is explained by the Big Bang theory, which gained prominence in the early 20th century. It posits that the universe began from a singularity and has been expanding ever since. The future fate of the universe hinges on the nature of dark energy, a theoretical force believed to drive this expansion. Current estimates put the age of the universe at just under 14 billion years. Depending on dark energy's density, the universe's expansion may continue indefinitely, or it might slow and reverse. Two possible scenarios for its future are the Big Rip and the Big Crunch. In the Big Rip scenario, the universe's expansion accelerates until it tears apart all cosmic structures, from galaxy clusters to stars and even atoms. Conversely, the Big Crunch suggests that gravity might eventually overcome expansion, causing the universe to collapse back into a singularity. Each scenario carries profound implications for the future of existence as we know it. The eventual fate of the universe, however, remains uncertain and subject to ongoing scientific inquiry. Thanks for watching our channel. Like and subscribe our channel. Have a good day.